Hello everyone, I'm honored to give this talk today. I will present HangFix. HangFix is an automated software handbag fixing tool for production cloud systems. I'm Jingzhu from NC State University. I'm the final year PhD student and I will graduate in the coming year. If you have suitable jobs, please feel free to reach out to me. This work is collaborated with Ting from IBM Research, Helen Gu and Guoliang from NC State University. Software handbags are difficult to diagnose and fix due to the lack of debugging information. Software handbags often cause serious service outages to the system. For example, in 2017, British Airways experienced a serious service outage due to a software handbag triggered by corrupted data during data center failover. Another example is in 2015, Amazon DynamoDB experienced a 5-hour service outage due to analyst retries during improper error handling. What are software handbags? The handbags are the software bugs that cause unresponsive or frozen systems instead of system crashing. Let me use a real-world handbag example to illustrate how software handbags happen. In this HBase bug, when the data corruption happens, the recover list function always returns false. Then the infinite loop happens. When this bug occurs, all the systems become unresponsive. We present HangFix. HangFix is a domain-agnostic, bytecode-based software handbug fixing tool. HangFix takes the application bytecode and bug triggering test case as the input, and HangFix produces the patched application bytecode as the output. HangFix consists of 4 steps. The first step, hang function localization. HangFix leverages the stack trace to pinpoint the hang function. The next step, likely root cause pattern matching. HangFix matches the handbag to a set of commonly seen root cause patterns. Currently, we target 4 root cause patterns. The infinite loop caused by unexpected function return value. The infinite loop caused by misconfigured parameters. The infinite loop caused by improper exception handling, and blocking operations without any loops. The first 3 patterns are related to infinite loops, and the last one is related to blocking operations. The next step, patch generation. HangFix produces the patch based on the identified root cause pattern. HangFix adopts simple strategies to enable the system to jump out of the stack state. For example, HangFix throws exception, restores the default value, traces execution of loop updating, and adds timeout checking to fix the handbags. Lastly, HangFix validates the generated patch and produces the patched code. The first step, hang function localization. After a hang bug is detected, HangFix dumps the stack trace continuously. HangFix leverages the stack trace to pinpoint the hang function. We separate the discussion into infinite loop hang function localization and blocking hang function localization. As you can see in the figure, the stack trace shows the call stack occurred on each thread and the specific line of numbers that are invoked. Since this compressed bug is the infinite loop handbag, the different lines of the hang function, that is a copy function, are invoked at different timestamps. The MapReduce bug shows an example of blocking handbag. Inside this figure, we can see that the HTTP notification function is a hang function. Since this is a blocking handbag, the same line of the hang function is invoked at different timestamps. Based on the observations, we conclude that the hand functions repeatedly appear in the stack trace, and the root cause hand function is always on the top of the call stack. Next, I will introduce the 4 likely root cause patterns and the corresponding patching strategies. If the hand function contains a loop and the loop strat depends on the function's return value, we say this bug is the pattern 1 bug. To patch the pattern 1 bug, we insert checkers for the function's return value. We throw exceptions on the error value set of the return value. This Cassandra bug shows an example of the pattern 1 bug. We identify the drain function as a hand function. Inside this function, there is a while loop. The loop strat depends on the return value of the skip function. If the input stream is corrupted, then the skip function returns either 0 or -1. Therefore, the infinite loop happens. To patch this Cassandra bug, we insert checkers for the return value of the skip function. We use a local variable that is skipped to store the return value of the skip function. After analyzing the loop body, we infer that if the return value is non-positive, then the infinite loop happens. Therefore, we insert a checker says if the skipped variable is non-positive, we throw an IO exception with a useful log message. If the hand function contains a loop and the loop strat depends on a configurable parameter, we say this hand bug is a pattern 2 bug. To patch the pattern 2 bug, we insert checkers for the configurable parameter and we throw exceptions on the error value set of the configurable parameter. This Hadoop bug shows an example of pattern 2 bug. We identify the hand function as the copy-byte function. Inside this function, there is a while loop, and the loop strat depends on a configurable parameter, the buffer size parameter. If the buffer size parameter is misconfigured to 0, then the read operation is conducted on an empty array. Therefore, the bytes read variable is always set to 0. The infinite loop happens then, because the termination condition cannot be met. To patch this bug, we insert checkers for the buffer size parameter. After analyzing the loop body, we find that if the buffer size parameter is non-positive, the infinite loop happens. Also, the buffer size variable is used as an array size at line 77. So the buffer size variable should be non-negative. After intersecting the two value sets, we infer that if the buffer size parameter is equal to 0, then the infinite loop happens. So, we insert a checker after line 97, like this. If the buffer size parameter is equal to 0, we throw an IO exception with a useful log message. Since the copy-byte function is a public function which can be accessed by any user-defined classes, we also insert a checker inside the copy-byte function. If the hand function contains a loop and the loop strat updating operation is skipped due to some exceptions, we say the hand bug is a pattern 3 bug. To patch the pattern 3 bug, we conduct index tracing to monitor loop execution. We insert checkers of the loop index and we throw exceptions when the loop index is not updated. This Cassandra bug shows an example of pattern 3 bug. When the data file is corrupted, then the read with short length function throws an IO exception. The IO exception is simply ignored at line 140. It gives up the correct execution of a read with short length function. Also, it skips the execution of read long function. These two read functions both contain loop index forwarding operations. Then the while loop keeps reading data from the same location. The infinite loop happens then. To patch this Cassandra bug, we insert a loop index variable. The original value is equal to 0. We abstract the loop index forwarding operations from the two read functions. If the read with short length function is correctly executed, the loop index is moved forward 3 bytes. If the read long function is correctly executed, the loop index is moved forward 8 bytes. We also insert checkers inside the exception handling strategies. If the loop index is not updated, then we throw an exception to jump out of the loop. If the hang function contains blocking operations without a loop, we say the hang bug is a pattern 4 bug. To patch the pattern 4 bug, we put the blocking function into a callable thread, and we add a timeout mechanism to the callable thread. This hive function shows an example of pattern 4 bug. Inside the hang function, that is a decompress function, there is a blocking operation, the inflate function. The inflate function blocks in the underlying GNI code. To patch this bug, we replace the inflate function with inflate with TO function. We put the inflate function into a callable thread, as shown here. And we leverage future.get method to add a timeout mechanism. The timeout value is configured here. To remind you our system design again, we have gone through the hang function localization, likely root cause pattern matching, and patch generation. Now we move to patch validation. To validate the generated patch by HangFix, we rerun the existing hang bug detection tools, we rerun hang function localization tool, and we run the application's regression test suites. If the hang bug does not occur again and all the regression test suites are passed, we say the patch is valid. Our evaluation consists of two parts, an empirical study and an experimental evaluation. For the empirical study, we have collected 237 bugs. We have quantified the generality of 4 root cause patterns, and we have evaluated whether bugs falling into the 4 root cause patterns can be fixed by HangFix completely. For the experimental evaluation part, we have reproduced 42 real-world hang bugs. We have evaluated HangFix performance from fixing results, fixing time, and patches overhead. This pie chart shows the empirical study results. The results show that the 4 likely root cause patterns cover 76% bugs. We also identified 4 other root cause bug patterns that are missing unlock, risk-induced infinite loop, risk-induced blocking, and deadlock. These 4 bug patterns are all related to synchronization or concurrency. We also evaluated whether bugs falling into the 4 root cause patterns can be fixed completely by HangFix. The empirical study results show that among the 180 bugs, 136 bugs can be fixed completely, and 44 bugs are partially fixed by HangFix. To fix the 44 bugs completely, we needed to insert application-specific operations, or we needed to restore the system's state. For the experimental evaluation, we have reproduced 42 bugs. These 42 bugs occur on 10 cloud server systems. We also list the number of closed bugs and the number of open bugs occurred on each system. To summarize, we have reproduced 14 closed bugs and 28 open bugs. The experimental results show that 15 bugs belong to pattern 1. 7 of them can be fixed by manual patches and all the 15 can be fixed by HangFix. 13 bugs belong to pattern 2. 2 of them can be fixed by manual patches and all the 13 can be fixed by HangFix. 6 bugs belong to pattern 3. 2 of them can be fixed by manual patches and 5 of them can be fixed by HangFix. 8 bugs belong to pattern 4. 3 of them can be fixed by manual patches and 7 of them can be fixed by HangFix. To summarize, we have reproduced 42 bugs. 14 of them can be fixed by manual patches and 40 of them can be fixed by HangFix. HangFix can fix both closed and open bugs. We also list other experimental results from two aspects: the fixing time and the additional CPU overhead after applying HangFix patch. The fixing time ranges from 0.7 to 22 seconds. HangFix fixing time depends on the intra and inter-procedure analysis. Note that developers often take several weeks or even longer to provide manual patches. It might be unfair to directly compare HangFix fixing time with manual fixing time, because HangFix is an automatic fixing tool and manual patches involve manual efforts. However, we believe that HangFix can help developers to fix software hang bugs in massive cloud systems efficiently. After adopting HangFix patches, the additional CPU overhead is less than 1%. It is because, compared with the original root cause function, HangFix only inserts certain checkers to the function. Those checkers can impose little overhead to the system. To conclude, HangFix is a domain-agnostic, bytecode-based hang bug fixing framework. HangFix describes a hang bug root cause pattern matching scheme. HangFix presents an automatic HangFix patch generation system. We have conducted an empirical study over 237 real production hang bugs, and we have evaluated HangFix over 42 hang bugs on 10 cloud server systems. We want to thank all the reviewers for their valuable comments. This research is supported in part by 2 NSF grants. That's all. Thank you for listening.